Welcome back. In this lesson, we will talk about the intellectual history of software-defined networking, which spans more than 20 years. Although excitement about software-defined networking has increased over the past few years, many of the ideas have evolved over the past 20 years. Indeed, the term software-defined networking was coined in 2009, but many of the ideas have roots in earlier technologies, dating back as far as the phone network. You can read more about the material that's covered in this lesson in the article that's linked below. We can think about the intellectual history of software-defined networking as proceeding in three stages. Active networking, which introduced the notion of programmable networks. Control and data plane separation, which offered open interfaces between control and data planes. And the OpenFlow API and network operating systems, which was the first instance of widespread adoption of an open interface between a control plane and programmable routers and switches. For each of these stages, we'll talk about the intellectual contributions of that stage, as well as various myths and misconceptions surrounding that technology. Active networking came at a time when the internet was seeing much more diverse applications and increasing use. Researchers wanted to deploy new ideas, and active networking was the first attempt to make networks programmable. It was pushed by a reduction in computing costs, as well as much interest from funding agencies. On the other hand, network operators were frustrated with the difficulty in deploying new technologies in the network. The intellectual contributions of active networking included the notion of programmable functions in the network virtualization, the ability to have a packet demultiplex into software programs that were sitting on routers and switches in the network. And although it was never realized, active networking did offer a vision of a unified architecture for middlebox orchestration, which we're now seeing come to fruition in technologies such as NFV, or network functions virtualization. There are many myths surrounding active networking as well. One is that many people thought that active networking implied that an end user would always write programs that went into packets. In fact, most researchers working in this area recognized that this programming model would be pretty rare. Another myth of active networking was that many thought that packets must carry Java code. In reality, active networking had an alternative programmable router and switch model that looks not too dissimilar from many of the SDN architectures described today. Technologies that explored separating the control and data plane in the network took a shift towards pragmatism, attempting to provide programmability but tackling it in the context of a much narrower scope of network management problems such as traffic engineering. Working groups in the IETF, such as Forces, developed open interfaces between control and data planes, and other researchers also developed technologies for logically centralized control, such as the routing control platform. On the other hand, many network operators had pressing network management problems to be solved. Many of the initial architectures that offered control and data plane separation tackled a very specific network management problem. Control and data plane separation offered two important intellectual contributions. The first was the notion of logically centralized control, using an open interface to routers and switches. The second was technologies and algorithms for achieving distributed state management across a distributed set of network controllers. There were several myths surrounding control and data plane separation as well, but perhaps the most important myth was that logically centralized control violates fate sharing somehow. In fact, many conventional distributed routing solutions, such as OSPF areas and BGP route reflectors, already violated these principles. And somewhat paradoxically, introducing a further separation of data and control planes allowed researchers to think about distributed state management in much cleaner ways than they were able to in the context of existing routing protocols and technologies. OpenFlow took a much more general approach, providing more functions than earlier route controllers and building on existing switch hardware support. Relying on the support of existing switch hardware limited flexibility somewhat, but offered a huge win in immediate deployability. In some sense, OpenFlow was pushed by a perfect storm between network operators who faced real network management problems, vendors, many of whom were eager to unseat incumbent vendors, chipset designers who'd begun to open their APIs, and researchers who are looking for new ways to innovate in the network. OpenFlow was initially adopted in campuses and then in data centers. Now we're seeing many more deployments of OpenFlow in a variety of different networks. OpenFlow itself offered several intellectual contributions. One was generalizing the network devices and functions that Control Data Plane could support. A second that came in conjunction with OpenFlow was this vision of a network operating system with 3 layers: a data plane with an open API, a layer for managing state, and a third control logic layer that affected the data plane based on the state of the network. These network operating systems also develop new distributed state management techniques. There are several myths surrounding OpenFlow as well. One is that many thought that the first packet of every data flow must go to the controller. And in fact, OpenFlow makes no assumptions about the granularity of rules or whether the controller handles any traffic at all. The second myth is that the controller must be physically centralized. In fact, most real deployments have distributed controllers. And the final myth is that SDN and OpenFlow are equivalent. In fact, OpenFlow is just one instantiation of SDN. Our intellectual journey has offered several lessons, but perhaps the most important is that of balancing vision and pragmatism. OpenFlow, in some sense, took off in part because it found a sweet spot between the vision of a programmable network and the pragmatism provided by support from existing hardware. This tension continues as we seek to extend the notions of SDN and network control to other parts of the network, including the desire to extend network control to commodity servers, as well as the trends towards making data planes increasingly programmable. As we extend the notions of SDN to these other parts of the network, it will be important to keep the balance between vision and pragmatism in mind.